Hello, my name is Pedro Rivero, and I'm a PhD student at Illinois Institute of Technology doing research at Argonne National Lab. Today, I'll be talking about an optimal quantum sampling regression algorithm for variational eigensolving in the low qubit number regime. So let's get started. As many of you may know, the variational quantum eigensolver, or VQE as it is most commonly known, is the most widely used algorithm for variational eigensolving. By nature, it is a hybrid quantum classical algorithm, meaning that it not only uses quantum resources, but also classical ones for solving a given optimization problem. Actually, the way it works is rather straightforward. It simply embeds a quantum processor unit within a classical optimization loop. Said quantum chip is then used for performing the most costly operations in the optimization scheme, namely evaluating the target function, which usually is quantum in nature. A typical optimization cycle would work as follows. First, the quantum computer prepares a quantum state according to a given set of parameters provided by the CPU. This can be easily achieved through the quantum circuit formalism. Then, a number of measurements are taken, and from those measurements, the expectation value function of the target operator is calculated classically. Finally, the classical optimizer decides if convergence has been achieved or if it needs to provide a new set of parameters to start off a new cycle. This is then when we run into problems. Because of the way we currently access quantum processors, that is, over the cloud, we need to establish an internet connection on every cycle of the optimization loop. This introduces a pronounced bottleneck which greatly increases the time required to run algorithms on actual hardware. To address this issue, we have come up with a new algorithm based upon Fourier analysis of the expectation value function that we want to optimize. Quantum Sampling Regression, or QSR for short, first determines the number of samples that need to be taken for every parameter in the parameterization ansatz. This is accomplished by analyzing the topology of the quantum circuit in charge of implementing said parameterization, and therefore coming up with an associated bandwidth. Thanks to this, it can then request all necessary samples to the quantum processor in just one go. Next, it uses those samples to reconstruct the expectation value function classically as a trigonometric series. And finally, it performs optimization on this newly created regression function. The optimality of our technique is proven by the Nyquist-Shannon sampling theorem, which establishes a theoretically minimum amount of samples to reconstruct any given function. Since VQE is thought to be valuable only for limited quantum computational capabilities, otherwise better algorithms such as phase estimation would be available, we came up with an algorithmic complexity model to compare its performance with that of QSR in the low qubit number regime. The results that we obtained pointed at a threshold above which VQE outperforms QSR, but also showed a regime in which QSR is more efficient. The extent of this regime will vary from problem to problem, and we provide heuristics to help determine it in each case. Other applications of our novel algorithm are oversampling to attain higher precision, undersampling to boost performance and get rid of small wavelength oscillations leading to burdensome local minima. In this regard, QSR could be used as a low-resolution startup supplement to VQE. Also, as a proxy to transition between simulators and real devices. This is so because we will be improving convergence by getting rid of stochastic behaviors while still retaining important quantum computational features. Finally, we will be able to use it in order to work with quantum functions classically, without resorting to the exponentially hard matrix formulation of quantum mechanics. To wrap up, as a benchmark problem, we reproduced the binding energy of the deuterium atom using both VQE and the QSR algorithm. Particularly, we implemented an oversampling strategy for QSR, and just as predicted, the results that we got actually outperformed VQE in terms of the error rate. Not only that, but in the two cases that we studied, QSR required far less samples than VQE and even less queries to the quantum processor. And with that, I would like to thank the Chicago Quantum Exchange and the US Department of Energy for supporting this work, and to you all for tuning in today. Make sure to reach out if you have any questions. Thank you.